We can wait for 1 minute.
Shall we start?
Yeah, sure, sir. You can start, sir.
Good afternoon, everyone. Myself, Ankit Kumar. I am president of Northern Council, Association of Indian Physics, and I welcome you all to third lecture of organized by Association of Indian Physics. And today's talk on to the journey of small world into a quantum realm by Dr. Sonali Patnaik. And first of all, I would like to invite Dr. Sanjay Kumar Singh, who is founder president of AIP, to give an introductory speech. Over you to Dr. Sanjay sir.
Yeah, thank you so much, Sir Ankit, sir. Good afternoon, on and all. On behalf of Janardhan Singh Foundation, that is JS Foundation and Association of Indian Physicists, AIP, I, Dr. Sanjay Kumar Singh, founder president of AIP, heartily welcome you all. I also will welcome Dr. Sonali Patnaik, speaker of today talk, who is also president of AIP Research Order. Captain Rituraj Singh, president of AIP Central Council, will chair the today's session. And other council members, respected faculty members, research scholars, and students from all over the country. I'm very grateful to you all for your talk. I would like to give brief introduction about our association. Nikhil, first slide, please. So I would like to I would like to give brief information about our association. So the objective of our association is to provide a platform for youth, young peoples of nation who is highly motivated in physics to make great nation using experimental exposure in school, colleges, and universities. With this objective, EIP organizes multiple activities like talks, seminars, conference, research-oriented meetings, discussion, presentation, debates, laboratory workshops, and competitions for teachers as well as students. Next slide, please. So the Association of Indian Physicists, AIP, is a subdivision of Janardhan Singh Foundation, that is JS Foundation, registered under MCA, Government of India. Its branch office is in Barnala, Punjab, which have 2 office bearers. It consists of physics teachers, researchers, and other persons who are interested in spreading of scientific knowledge, promotion of scientific temper and culture, with a focus on improvement of quality of physics education at all levels. So to achieve efficient outreach, it has sectioned the nation into over 5 regions, that is North, South, East, West, and Central Council. Next, please. These are the council members of association who is providing great efforts to youth and faculty members of the nation. Next, please. So thank you so much, all members who have joined today. Do help who need help. This is the quotation of myself, and be changers to the society for the society. If anyone from the members of today talk who want to join our association, they can text message, or you can send personally message on WhatsApp so that we can proceed. Now, we would like to over the Dr. Captain, over to you. Your mic is off. Dr. Captain, your mic is off. Please unmute. Dr. Captain, your sound is not audible. Please have a patience for some minutes. Dr. Captain, please unmute and start the introduction of today's speaker. Still, your mic is unmuted. All the participants are requested to wait for a minute. Captain, your mic is muted. Please check.
Captain sir, can you join from Dr. Sanjay's account, the main association's account?
Sonali ma'am, you can now share the screen. In the meantime, you can share the screen.
Sanjay sir, if you allow me to, I can introduce our today's speaker.
Yeah, sure. You can proceed because I think there is a technical issue with Dr. Captain.
Yes.
Yeah, so you can give the introductory part of that today's speaker.
Yeah. Yes. So I would like to invite Dr. Sonali Patnaik, who is currently postdoc fellow in National Institute of Science Education and Research in Bhubaneswar, Odisha. She has done PhD graduate in theoretical physics, and she has also an impressive academic and teaching background. Earlier, she joined as a guest faculty in Odisha University of Agriculture and Technology, where she taught students at various levels for 2 years. Dr. Patnaik's expertise also includes mentoring postgraduate projects in theoretical physics. Her research focuses on unraveling the wonders and puzzles of the universe through theoretical particle physics. And her today's talk is to the journey of to the small world through the quantum realm. And I would like to now invite Dr. Sonali Patnaik. Ma'am, over to you.
Sonali
Sonali
ma'am,
ma'am.
your mic is muted.
Hello.
Yes, you're
Yeah,
audible,
you are
ma'am.
audible.
Okay, so my screen is visible.
Yes, ma'am.
Okay, so a very thank you to Ankit sir for giving such a great introduction. I guess there's an echo of my voice. So can we just slow it down? Hello.
Ma'am, ma'am,
I
the
think
echo
it's
is now
okay now.
managed.
Okay.
You can
So
proceed.
yes. So today is third talk of our AIP, and today I would like to give you all a flavor of the most fascinating subject of science, that is the quantum physics. And before proceeding, here I would like to say that today's talk is basically on the basic foundations and the historical point of view of quantum mechanics, because I'm not going into the details of mathematics because I have to take care of all the levels of audience present here today. And also, I have to confine it within 30 minutes as the subject is very vast. And, anyways, you can always do the mathematics in your individual classes or lectures. So, yes, the most fascinating phenomena, the quantum realm, the studies of this subject is based on the subatomic level. And this is the approach one should always follow before studying quantum mechanics. And these are the famous lines which are taken from Shakespeare Act, where Horatio is saying, "Oh, day and night, but this is a wondrous strange." To which Hamlet is replying, "And therefore, as a stranger, give it a welcome. There are more things in heaven and earth, Horatio, that are dreamt in your philosophy." So yes, quantum mechanics is one such a wondrous strange, and as a stranger, we should give it a welcome. And if at all we do not understand it, then again we have a famous quote from Richard Feynman, who is saying that, "I think I can safely say that nobody understands quantum mechanics." So this can be the second motivation to proceed to study quantum physics. Okay. So the theories of quantum physics started with set of mysteries in late 1800, or I can say in early 1900, where realities did not quite matched with the older theories of physics. And now the older theories of physics are known as the classical physics. So classical mechanics is a subject which is the oldest part of modern physics, which deals with the description of macroscopic objects. And classical mechanics is based upon Newton's laws of motion. These are the founding fathers of classical mechanics: Galileo Galilei, Huygens, Isaac Newton. And classical physics is also based on Maxwell's electromagnetic equations and theory, where any amount of energy is emitted or absorbed continuously. And therefore, it is also known as Newtonian mechanics. Again come to this difference later. So this was physics around 1900, where the ideas of Isaac Newton continued to provide foundation of physics. From the perspective of 1900, it looked like physicists had managed to understand all the phenomena in our world. But there were several mysteries which led to failures of classical physics, or which we can say became the backbone or foundation of quantum physics. So first is the atomic spectra. As we all know, when light shines through a gas, it emits different kinds of frequency of light, which is known as distribution. This particular thing, atomic spectra, could not be explained in terms of classical laws of physics. Then there were a lot of confusion about stability of atoms, because according to classical physics, electrons will continuously emit energy, and as a result it will collapse and fall inside the nucleus, but that is not happening. Electron is revolving around the nucleus, and that could not be explained by classical laws of physics again. There was again radioactivity, which could not be explained from classical point of view. Then there was this famous black body radiation demonstrated by Max Planck, where you can imagine a black body, for example, a sun, which is emitting continuously electromagnetic radiations, and the distribution is known as black body distribution. And this particular distribution could not be explained again from classical laws of physics. As we can see, when we plot a graph intensity versus wavelength of that distribution, we see that the experimental data are quite different with the classical laws of physics. So this was the failure, one of the major failure, or one of the major foundation of quantum mechanics. Then there was this photoelectric effect experiment. So what is this experiment? When you shine a light on a metal surface, an electron is ejected out. So this particular experiment also didn't say about that light is a wave, which is a classical concept. So according to classical physics, we knew that light is a wave, but this photoelectric effect could not say that. The experiment said that light consists of stream of particles known as photons. According to classical physics, so this is the wave which holds properties like wavelength, frequency, velocity, oscillations. We have ocean waves, sound waves, radio waves. So this was the concept of wave. But photoelectric effect could not say that light was a wave. So then came Albert Einstein in 1905, who postulated that light consists, or light is made up of individual pieces known as quanta or photons. According to Einstein, low frequency light is made up of low energy photons, and high frequency of light is made up of high energy of photons. And his postulate or his thought was radical in a sense that he said that light was both wave as well as particles. This was the quantum revolution and where the quantum theories were born. So quickly summing up about photoelectric effect, the photoelectric effect provides evidence for the particle nature of light. The experiment also provides evidence for quantization. Now, what is quantization? Anything which comes in integral multiple. Like if I say energy is quantized, I will say that energy comes in integral multiple, like 2i's of energy, 3i's of energy, 4e, 5e, 6e. That is what I mean by quantization. So if light shines on surface of metal, then there is a point at which electrons are ejected from the metal. The electrons will only be ejected once the threshold frequency is reached. Below the threshold frequency, no electrons are ejected. And above the threshold frequency, the number of electrons ejected depends upon the intensity of light. So this became the backbone of quantum mechanics, the photoelectric effect. Now, these were the founding fathers of quantum theory, the three key experiments that led quantum mechanics to begin. As I said earlier, Max Planck, who demonstrated the failure of black body radiation. Then Albert Einstein, who understood the challenge to classical physics and developed a theory where he said that light is composed of particles known as photons. And then there was Niels Bohr, who understood the stability of atom, and he postulated Bohr model of atom in his theory. And now this is the famous photograph of this century, where group of brilliant minds met in a Solvay conference who developed the theory of quantum mechanics. So here we can see Max Planck is sitting here. Then there's this gentleman, Albert Einstein. Then modern quantum theories were developed by Paul Dirac, who is here. And then there's Pauli, there is Heisenberg, there is Lorentz. I guess you know Lorentz transformations you will be using. And then the only woman sitting here in front, the only lady who has won 2 Nobel Prizes, Marie Curie, one in chemistry and other in physics. So these group of people were developing and working on the most difficult problem of physics at that century. And of course, there are other group of scientists who are not here and who has also contributed to quantum mechanics. So up to this, we came to a conclusion that yes, light is a wave and also has a particle nature. Now, there comes a question that can material particle exhibit wave nature? Like light, which is a wave concept, can have particle nature. Can material particle exhibit a wave nature? So Louis de Broglie in 1923, he proposed the material particles should exhibit wave properties, and he postulated it as the matter waves. Matter, as in electrons, protons, neutrons, consist of wave properties, and there began the wave particle duality. So he got inspired from Albert Einstein's papers, and he wrote his doctoral thesis in wave particle duality. So according to that, de Broglie formulated a famous equation known as de Broglie's equation, where lambda is equals to h by p, where lambda is the wavelength, h is the Planck's constant, whose value is 6.626 into 10 to the power minus 34 joule second. P is the momentum. So this was the famous wave equation, the equation, de Broglie's equation. And with this equation, now I can ask a funny question. So are you a wave? According to de Broglie's, it's yes, because every matter particles consist of wave. But when it comes to macroscopic objects, it becomes negligible. Why? Because according to this equation, lambda is equals to h upon p, where p is mass into velocity, the momentum. So wavelength is inversely proportional to mass. So when we increase the size of the object, the wavelength decreases. And when we decrease the size of the object, wavelength increases. So you are a wave, but it is very negligible as we are very larger in size. And for example, if we take electron, whose mass is 9 into 10 to the power minus 31 kg, moving, let's say, 10,000 kilometer per second, has a wavelength of 10 to the power minus 10 meter, which is a size of atom. So this is the scale where quantum physics comes to play. So quantum physics, the domain of quantum physics is the subatomic level. So with this, again, I give it a short map that light, which we know is a wave, is also have a particle nature, and particle also have a wave nature along with its particle nature. So this is the wave particle duality. And as in this scale, we can see that quantum physics lies in the domain of 10 to the power minus 10 meter of order. And when we increase the size of the objects, it tends to become classical physics. So I hope little bit of idea you have got till now. And by wave particle duality, I mean this. This how it should look if I say wave particle duality. It's both. Light is a wave as well as it has a particle. So this is how a particle moves in quantum theory. So in quantum mechanics, particles are actually superposition of waves, a group of superimposed waves which are moving together. And to understand the physical properties of this moving particle, mathematically it is represented by a wave function, and by Greek letter it is known as psi. So this is the mathematical expression of the particle of wave, that is a wave function. And wave function physically gives information about everything of a state of a system. Okay. So by that time, there was no clue that how to make sense of quantum waves. Like what is actually wave particle duality? Therefore, in 1925, Max Born made a very bold claim. He made a sense that quantum waves had no choice to interpret them in terms of probability. So this was the basic difference between classical physics and quantum physics, because quantum physics is a probabilistic theory. We cannot determine the specific position of a particle. We can only predict its probability of being there. So this is the real nature of quantum physics, probabilistic nature. And therefore, as I always had said, that classical world is deterministic. but quantum world is probabilistic. In classical physics, we can always know the position and velocity of object at a particular time using Newton's laws of motion. But quantum mechanics is a probabilistic theory. It is impossible to know position and velocity with certainty at a given time. Only probability of future state can be predicted. And this led to a very famous equation, that is the Heisenberg uncertainty principle. In 1927, Werner Heisenberg generalized this quantum fizziness into what is known as uncertainty principle. So here delta x is uncertainty in position, delta p is uncertainty in momentum. So the product of delta x and delta p is greater than equals to h by 4 pi. H is the Planck's constant, as I mentioned earlier. So this equation means that if we precisely locate an object, then there will be more uncertainty in the predicting the momentum of the particle and vice versa. Similarly, we can hold this relation for energy and time as well. So delta E is uncertainty in energy and delta T is uncertainty in time. So product of delta E and delta T is greater than equals to h upon 4 pi. So this is the uncertainty principle, one of the basic foundation of quantum mechanics. And now proceeding to postulates of quantum mechanics, which is incomplete if I do not mention this. So the first postulate of quantum mechanics says that every physical realizable state of a system. Now, state of a system, I mean any electrons in a metal or semiconductor, any physical system like photon or conduction of electrons. So any physical realizable state is described in quantum mechanics by a wave function known as psi. So this is the wave function, when I say, which contains all accessible physical information about the system in a state. So accessible information, I mean the information we can extract from the wave function. And wave function, it is a function of position, momentum, energy that can be easily localized. Second postulate says that in quantum mechanics, if we take the square, the modulus of psi square, we get probability of that particular state. So to find any particular position of a particle in a state, we can always find its probability. And probability that in a position measurement at time t. And third postulate says that every observable in quantum mechanics is represented by an operator. So in detail, a little bit of mathematics I will be using here. So as I say, wave function, first of all, it is a complex function consisting of real part and imaginary part. Okay, so wave function is a complex function. It describes the state of a system. And from here, we can see this blue line represents the real part of wave function. This represents the imaginary part of the wave function. And the solid black line represents the probability of particle to be found in this region. So this is the reason where the particle can be found. This is the probabilistic nature. Now, we can always connect the wave function to observable. And by observable, I mean velocity, I mean position, I mean momentum, energy, etc. So as I said, according to third postulate, every observable is connected with an operator. So in quantum mechanics, we use operators and it is represented by hats. So here we can see X is a position operator and we spell it out as X cap. P is momentum operator, we spell it out as momentum P cap. Okay, so this is how it is represented. So now if we operate X position operator to the wave function, so this is how we operate. Now you will ask me, is it same as psi X cap? No, it's not the same. Operator always act from left hand side of the wave function. So it's always position operator into psi. So if I say, let's say my position operator x cap is x. Let's say psi is a polynomial of second order x square plus 2x plus 2. So what will this position operator do? The x will multiply with the wave function, with the polynomial. Similarly, this is the momentum operator where p cap psi, which is also not equals to psi p cap. Remember always, the operator is always acted from the left-hand side to the wave function. So p cap momentum operator is minus IH cross derivative into derivative with respect to x. That is d on dx. So these are some observables. This is the energy operator. Position is represented as x cap. Momentum is represented as p cap. Energy is represented as E cap, which is equals to P square by 2m, and so on and so on. So these are the basics of quantum mechanics. So then there comes a famous Schrodinger equation, Erwin Schrodinger, who again inspired from Freud's proposal, and he gave an equation for matter waves. This is a partial linear differential equation which gives information and which determines completely the behavior of wave function, right? So in this equation, we can see its I is the imaginary, IH cross. This is del on del t, which is operating upon wave function. And wave function is a function of space and time. X is space, t is time. Here again, minus h cross by 2m. M is the mass of particle. Then there is this second derivative. V is the potential, which is again a function of space and time. This is operating upon the wave function. So if we see again a map, so we have operators, we have Schrodinger equation, and we have wave function. So we add operator on wave function, and instead we get observable. When we act operator on wave function, we get observable. And by observable, I meant position, velocity, energy, momentum, etc. Operators are again used in Schrodinger equation. And solving Schrodinger equation, we get solution in the form of psi, which is wave function. And taking a mod square of it, we get always the probability of finding the particle at that particular region. This is the basic foundations of quantum mechanics, and quantum mechanics should always revolve around operators, Schrodinger equation, and wave functions. So this gives a basic difference between classical and quantum. So classical physics, basically, as I said, it's a deterministic equations. They are well-defined equations and whose measurements can be precise. But quantum systems can always be described by wave functions, probability densities, and the Schrodinger equation, the equation of motion. Then I would like to come to a very interesting phenomena of quantum physics, that what is meant by collapse of wave function. So this I would like to say here because in my next, this has a relevance to my next slide, where I will be showing the 2022 Nobel Prize winning for the groundbreaking research and experiments in quantum mechanics. So this has a relevance to there. So just hold on, it's becoming more interesting from now on. So what do you mean by collapse of wave function? Quantum mechanics is always deals with the measurement. So let's say we want to measure a particle at position, let's say XA. Okay. Before measurement, this is the wave function, which means the particle can be in these regions. Okay. At one particular region. But we want to find the particle at XA. So what we do? We measure the wave function. Now, once we measure the wave function, it jumps from the state of being simultaneously in all positions to a state with definite positions at XA. This is the magic of measurement. This was before measurement. Particle was everywhere. We won't know. We do not know where the particle is. After measurement, it collapsed to a single entity. which means the measurement is causing the collapse of a wave function. This is a very interesting quantum phenomena, and which has a good analogy with the Schrodinger's cat paradox. So what is this? This is an interesting thought experiment which states that, let's say you take a cat in a box and something that will eventually kill it. Let's say a poison is there inside the box. So before measurement, you do not know whether the cat is alive or dead until you open the box. Once you open the box, means you are measuring, the wave function is collapsed, and now you have the answer, the cat is either dead or alive. But before measurement, the cat is in superposition state of alive plus dead. This is the interesting aspect of quantum physics, that measurement, what is happening at the measurement. So you can see, this is before measurement, and after measurement, don't know. God, even today, there is a big question. What is happening to the wave function? How it is getting collapsed? So as I said, this has a relevance with the Nobel Prize winners of physics in 2022. These three gentlemen worked on groundbreaking research and experiments on quantum mechanics. John Clauser, Alan Aspect, and Anton Zellinger. So I would like to give a brief idea on the study. They brought this into limelight. This is a very interesting phenomena. Let's say we have a source particle. Okay. So we have a source particle having zero angular momentum, having zero spin angular momentum, right? Now this source particle is being splitted into two other particles. The source particle is being split into two other particles. According to conservation of angular momentum, we can say that these two particles will also have zero angular momentum, because the source particle have zero angular momentum. And if from the source particle, these two particles are coming out, we can say that these two particles will also have zero angular momentum. Or we can also put it in this way: if the direction of the first particle to be in anti-clockwise, then the second particle's direction can be in clockwise direction in order to cancel out, and they will conserve angular momentum. Correct? But quantum mechanically, what happens is, when we measure the direction of the first particle, when we measure the directions of the first particle and it came out to be anti-clockwise, automatically the second particle are measured in clockwise direction. So here lies the quantum argument. How does this second particle know that the first particle is being measured? So this is kind of a spooky action going between two quantum particles, or some information is being traveled instantaneously. I hope you get the point. So I'm again saying it. So when we measure the first particle's direction, automatically the second particle direction has been measured in clockwise. So how do the second particle know that the first particle has got measured, even though they are separated with a long distance? This is known as quantum entanglement, and famously it is known as spooky action. So to give it a logic explanation, Albert Einstein with his colleagues Podolsky and Rosen, which is famously also known as in a short form EPR paradox, Einstein stated that some hidden variables are there between these two particles, which has not yet been explained. And therefore, according to Einstein, quantum mechanics is an incomplete theory, and which relies on the principle of locality. By locality, he meant things that is not instantaneous and things which travels with speed of light. Okay. So Einstein stated that some hidden variables are there, which has not yet been explained, and this particular theory is within local. This is a local theory. But John Stuart Bell, he came in 1964. EPR paradox was around in 1938, and in 1964, John Stuart Bell, he disproved Einstein, and he famously said, or he postulated, using his Bell's inequality, he said that there indeed exists some quantum phenomena where there is no such theory called as local. So John Bell, he said that this is not a local theory, this is a non-local theory. Non-local, he meant this is an instantaneous process and things which travel more than speed of light. So this was given by John Bell. He proved it with the help of a lot of experiments in his lab. And he proved this. In 1964, he postulated this, and in 1968, John Clauser, he came and he read the paper of Bell's inequality or Bell's theorem. And for the first time, he demonstrated the experiment in the laboratory. And indeed, he showed that, yes, there is some spooky action is going in between two quantum particles, and some quantum phenomena or quantum information is being traveling instantaneously. Then in 1972, Alan Aspect and Anton Zeilinger, they came, they improved the experiments, and Anton Zeilinger, he gave quantum teleportation. And by quantum teleportation means a way of transferring information between two quantum state of particle situated at a long distance. So this is the timeline of getting a Nobel Prize. And then in 2017, they first demonstrated the experiment, which came out true. And for the first time, they disproved Einstein that no, it is not a local theory. It is non-local, where information is traveling instantaneously. And then in 2022, they won the award. So in the audience, anybody who is dreaming of getting a Nobel Prize can calculate how much patience you have to keep. And of course, the love for the subject. Because EPR paradox came in 1938. Then 1964, John Bell gave his postulate. And unfortunately, tragically, he passed away. Otherwise, he could have get the Nobel Prize. And then in 1968, 1972, and 1982, Clauser, Alan Aspect, and Anton Zeilinger, they came forward and they did experiments for the first time. But they showed that this quantum weirdness is there. But what is happening during the measurement, this is still a big question mark today's also. So with this, I would like to quickly say about the application of quantum mechanics in different fields of research. So quantum mechanics also applies to condensed matter physics, quantum biology, cold atom physics, quantum chemistry, nuclear physics, particle physics, quantum theory. Condensed matter physics is the subject where it deals with large system of atoms. So quantum rules are applied to the transistors, the superconductivity, and all. Again, quantum rules are applied to the biological systems such as photosynthesis. The GPS also uses quantum rules to navigate bird navigations, and quantum rules are also used for sense of smell and sight and the enzymes or catalyst. Quantum rules or principle are also used in cold atom physics, that is at ultra low temperature physics. This is where it has been used, like Bose-Einstein condensate and other states of matter. Then quantum physics is again used in nuclear physics, nuclear fusion, nuclear fission. Quantum physics is also used in chemistry. The quantum rules are used in chemistry, like it is used to determine the electronic structure, molecular dynamics, quantum Monte Carlo method, some simulations. And then it is used who study the particle physics. So this is the branch of physics which deals with the dynamics of the subatomic particles, the quarks, antiquarks, particles, fermions, bosons, and etc. And then these are the quantum technologies where the quantum rules are used, that is superposition and entanglement rules have been used in quantum cryptography. So quantum cryptography it's a way to secure information between two distances. So this uses qubits, or known as quantum bits, 0 and 1, which forms the basic foundation of quantum computer or quantum internet, today's technology. And then this is quantum teleportation, which again uses the principle of superposition, Schrodinger equation, and entanglement principle. So quantum teleportation, as I said, it is a way of transferring information between two quantum states, which are situated in very large distance, of course, not in two different rooms. This is not a Star Trek. So this is quantum. These are this age quantum technologies, or this modern age technologies which have been using today. With this, I would like to conclude with the realms of physics. So here, as we can see, if we go in negative y direction, the size is decreasing. And if we go in positive x direction, the speed is increasing. So classical mechanics is the subject which remains in the domain of macroscopic object and things whose speed is less than speed of light. Quantum mechanics is the domain which lies in the field of microscopic or subatomic particles, but whose speed is less than speed of light. Relativistic mechanics are those corresponding to the Einstein's general theory of relativity, like study of planets, gravity, black holes, cosmology, where things are very large, but it moves with speed of more than speed of light. And quantum field theory again is a subject where we assume that particles are excitations of field, and which lies in the domain of subatomic plus more than speed of light. These are the four realms of physics. And then again, I would like to conclude with Shakespeare's statements that, yes, small things are indeed weird. It's a wondrous change, and we should always give it a welcome. Thank you very much for all your kind attention. And do ask questions, anything you want to.
Thank you so much, Sonali. Very nice talk. Am I audible now?
Yes.
Oh, so last time I think something happened, so my voice not coming through. It was a very interesting talk. It was a very interesting talk, very knowledgeable. So now session is open for question and answers. So questions, please.
I hope I didn't little later. I hope it's within time.
Yeah, it's fine. It's Sunday today, so in 5 hour time.
Not for the students.
Yeah. Okay.
So any questions?
Yeah, there is a question in a chat box.
Yes.
Amrit Sagar here asked, I have a query. The classical observers can also have operators kind of thing. Like if you know force, then you can operate the differential operator to get energy. You can write it as a differential equation and integrate it to get the quantities like position and velocity. So what is his query? I didn't get it.
I could not understand. Yes. Again?
You can read a question, but I don't know what is his query. He's telling something or asking something.
Is he here? He can unmute and ask.
Yeah, if it is there, he can.
Yes, ma'am.
Oh, hi.
Yeah, please ask.
Yeah, hi. So the thing is, like in quantum physics, we use operators very much while solving
Yes.
problems and kind of things. But in classical mechanics, also we can use the same idea of operators, and we can find the position, velocity, and momentum. We can find these also.
Yes.
And the
Yes,
formalism
yes.
seems quite similar with quantum physics. So
Yes,
why?
absolutely.
I mean, the quantum physics has a lot about it, but in classical physics, we actually don't discuss these operators in in bit detail, but we do that in quantum physics. So why is this so?
Yes, there are aspects of classical also, the classical things. Whatever I have said today, the same things are also in classical, even classical equations of motion. But then again, there are fundamental mysteries which could not explain classical physics. Like I said, black body radiation, that could not explain classical, because until then it wasn't known that light was a, for example, light. We knew that light is a wave, but then when Einstein came and he postulated that light is made up of particle, then he clearly could explain the black body radiation. Then Bohr also explained that if light is consisting of stream of particles, he explained the stability of atom. So with the use of quantum mechanics, some mysteries were solved. Of course, there are the analogies of classical physics and quantum physics, but after arrival of quantum mechanics, the mysteries were solved. So I guess this is the theory. We can rely on this theory as they have solved a lot of problems from classical view. There are classical computers also, but after the arrival of computer, it's being more precise, and we are using quantum computers today also. So there is always a analogy of quantum to classical, but then as lots of mysteries have solved, therefore we are relying on quantum physics more than classical. I hope I could give answer to your question.
I
We
mean, like,
cannot.
yeah, I'm
Yes.
saying that in the mathematics we are using in classical mechanics, and the mathematics you are using while doing the quantum formalism. So
Yes.
in quantum mechanics, do we require some more sort of sophisticated mathematics than the classical theory? I mean, the mathematics is different, or it is we are all enough with the present mathematics, and we don't require some more special mathematics to deal with the quantum problems.
No, there are certain mathematics, like as I said, wave function is a complex function, so you will always use complex numbers. So quantum mechanics always deals with these mathematics only, complex numbers and integration, complex integration, where classical, I don't think classical uses this approach. So even there is hypogeometric functions. When you will solve Schrodinger equations, you will use certain mathematics that in classical we do not use.
Ma'am, I would like
So
to
yeah, there is a change. Yes.
I would like to add a point here.
Yes.
As you, Sonali ma'am, already told that there is a main difference between classical and quantum mechanics is that there is size difference of the particle. The particle
Yeah.
the we observe in quantum mechanics are very small as compared to classical mechanics. So because of the size, there is probability in finding that particle. But in classical mechanics, we are 100% sure that the position of the particle is there. So that's why we don't use any operators in classical mechanics, but we have to use probability and different equations to solve the probabilistic equations.
Yes.
Uh,
Yes. That is also an answer, because quantum mechanics is always a probabilistic theory, which always deals with subatomic scale.
yes.
Okay. So any other questions?
I think there is a question in chat box.
People who are here can directly ask the question, so it's better that we can.
How can
are here,
meditation
they can-
not be explained by this theory?
I don't know.
There is different
There is
domain.
a
Like,
Domain. So
how can
Sanjay sir
meditation be
asking
explained by quantum theory?
by, yeah, quantum theory or this theory.
See, the main thing of quantum mechanics is it's always in superposition states. Like, it's there and it is not there. It's a probabilistic theory. So I can only say you can control your thoughts doing meditation, like some thoughts you can control and some you cannot. So
Actually, in physics, we talk about the material world, right? So either it's
yes.
quantum or classical, there are materials, there are matter. But when we talk about the meditation, there is no material, there are thoughts. There is no mass limited with, so there is no quantized thing in jhana or meditation. So there is no relation
Yes.
between them. So, should be different.
So may I request you all to on the camera to take a group photographs during the session. Ankit sir, please request all the participants from the all participants.
Yes. Please keep your camera on so that we can take a group photo. Dr. Sonali ma'am, can you please stop presenting?
Okay.
Still, everyone has not kept their camera on. I request everyone, please.
I don't think they want to show their face.
Please keep your camera on. Yes.
So Dr. Captain, Ankit sir.
Yes, my camera is on, but I think it got disturbed. So my photo got freezed in that posture.
Dr. Meena, Sanjay sir.
I have taken the screenshot, sir. You can switch
Yeah,
off your camera.
Okay, thank you.
There is one suggestion, or you can say that by Satya Sarup. So he's saying, sir, please share all the PPTs in the group that had been shared during the lectures so that it could be helpful to all the students as well as others. Satya and other participants, surely we will share the PPT. Further, we will share the recording of this lecture on the YouTube. You can watch it later if you need.
I think
If you have
Shivraj
any further question,
has question. I think Shivraj has question. Yeah, Shivraj, Mr. Shivraj, you can unmute yourself and ask the question.
So he can unmute and ask the question.
there is one question from Dr. Kodambari. He's asking how to use quantum mechanics in real life positions.
In real life,
Yes, ma'am.
like as I said, it's been used in quantum technologies are there, quantum computers are there, superposition principles are being using superposition principles, and then there is quantum entanglement principles. So these sort of principles are being used in technologies like quantum computers, quantum information, quantum communication. So these are today's daily day-to-day life where it's being used in communication. And also the superposition principle is being used as GPS system also. Yeah.
Yes, Kalyani Panayak.
Yeah.
Kalyani Panayak, you can ask the question.
Unmute and ask the question. Kalyani ma'am, please unmute your mic and ask the question.
We have another chat message, I guess.
No, ma'am, there is no question in chat
Okay.
box.
There is one question is here from Dr. Sangeeta. She is asking, discuss on quantum teleportation using quantum theory. Can matter move into future?
See, quantum teleportation, the only thing I know, because I am not doing research in quantum mechanics, so I can only say quantum teleportation is a way of transferring secure information between two entanglement particles or two quantum particles. So using this theory, and quantum theory is a different thing. Quantum theory and quantum teleportation is different thing. Quantum theory is the theory, the grand unified theory where we can use quantum mechanics and general theory of relativity, which has not yet been seen or discovered, which is known as quantum gravity, the unified theory of physics. So quantum theory is based on quantum mechanics and general theory of relativity. Whereas quantum teleportation is a different technology where the informations are being transferred from one location to other location, where the two particles are in different state. And now if you ask, can matter move in direction? Yes. There is time travel, but of course time travel is there, but we haven't discovered it yet, I guess. So this much I can say. You think, Rituraj, like time travel, how can we move matter forward? Can we use quantum theory in moving the matter forward, or
Don't know. Use.
Sonali, ma'am, there is another question in chat box.
Hello.
yes?
Hello. I have one question.
Yes.
Why quantum physics is so much complicated than the other branch of physics like nuclear physics or classical mechanics, electrodynamics?
Because we cannot see in quantum physics
Because
we cannot see what is happening. That is the only adding to the complication.
because with microscopic, is that the thing, or because we are here dealing with the here microscopic, and if we deal with other subjects, that is macroscopic, as we come to know. But why things
Sir,
are so much different than other subjects, other branches of physics?
because yes, as I
Because
said,
yes, please.
things are very small in quantum world. Like it is
Yes.
applicable to very small matter in the order of 10 to the power minus 10 meter. So very, very small.
Yes.
So when we are trying to find out theories of the things which are very, very small, so therefore complications are being arising. So like I said, there are experiments which is proving the quantum phenomena, but still there is a big question that what is happening to the wave function, what is meant by measurement, it's still been unanswered till date.
Yes.
So
Okay.
and therefore, and again, quantum physics is also a probabilistic nature. It is not giving a certain answers. So when probability is coming, so things are becoming more weird.
Yes.
And
Okay.
one more thing I would like to add: nuclear physics cannot be treated with the quantum mechanics. So you said that nuclear physics is easier than quantum mechanics, so it is not. I mean, either it is nuclear physics or it is any physics apart from classical physics. You need quantum mechanics to everywhere. So it is not complicated. It so depends on our understanding, how we understand the quantum mechanics. If you understand well, then it is fine for you, right? So those are teachers who make it interesting or boring than your interest. So that's why it become complicated or easy. So it depends upon one's study. So the people are working on quantum mechanics and they are doing quantum computing and many more things. So it's complicated than people want to do it, right?
No, we will come
So
across more theory, theoretical part in case of quantum mechanics. That little bit, uh, it is difficult for anyone to digest that. That that the thing.
Yeah, because
Basically, in quantum mechanics, what happened is that, you know, certain rules and the formalisms are there that
Huh.
which it is not obey in the case of the classical mechanics. So in
Okay.
order to explain the quantum phenomena, we use mathematical tools. As Sonali ma'am has said about the probability is quite
Hmm.
right. It is almost 100%. Now, giving an example to your question, say if you talk about the energy, okay, I'm taking the example from the point of material science. Okay, even material science need quantum
Hmm.
mechanics at all. Okay, there are a lot of theories
Yes.
out there which implemented with quantum mechanics, explaining the quantum phenomena. So you take as example, we know that the silver, okay, silver
Hmm.
is
Hmm.
if you check it, it will give certain. You go for your the photoluminescence, okay, it will give certain energy with certain color. But as the size decreases, what happens is that the color of that material changes. Got it? Like as an example, I'm talking about quantum dots. You might be heard about the particle whose particle size is ranging from 1 nanometer or from 0 nanometer to 10 nanometer. If you go through that, they will emit different type of color. Even a same material will give different color. Say if you, as an example, you go with the carbon quantum dots. Say you may synthesize from the grapes juiced or maybe lemon juiced, okay, and you prepare with different temperature, okay, then it will give different colors, but the materials are same. They are all carbon. Got it? So what happened is that in order to explain the different spectra, different color, we need to go for quantum confinement. Got it? So quantum mechanics is little bit tough. Yes, I do agree with that. But if you have a very good knowledge about mathematics, okay, then you could be very easy. Say to learn the quantum mechanics, the basic importance is you need to know about the differential equation. Most important differential equation, matrix, what we call as the linear algebra. Okay, you have good knowledge of the linear algebra, then quantum mechanics would be little bit easier for you. Okay, then regarding the measurement, okay, we cannot measure the preciseness. Okay, there will be an error of in order of Planck constant. Got it? In the order of Planck constant. So even though there is an error, we have to use it. We have to got it. And one of the question asked by the audience, I'm just adding to the Sonali ma'am. Sorry for that. Talking about the
yes,
time
yes,
travel. Okay, talking about the time travel. I have also spoken last time. Um, you might be heard about one of the particle, what we call as a muon. Okay, this muon particles is not generated or is available in the earth. Okay, it is coming from the deep space. Either it might be from the suns or somewhere from the heavenly bodies, whatever it is. But their lifetime is in terms of microseconds, not in a seconds. But there is a possibility that I am what I mean to say is that we are able to detect all those muon particles on the Earth's surface. What does it mean? It means that there is a time travel. Okay. So traveling time is possible, but there is a big doubt that whether it will travel in the past or future. That is again another topic, which is a uh, brainwashing topic. Okay, so please, what I would like to
actually, Deepak, I would not interrupt here. Beyond lifetime is time dilation. That is different thing. And the question he has asked about time travel. That is different concept, I guess. Traveling in time is different scenario. And time difference, time changing the time difference in one frame, depending on its velocity, that is different thing. Different thing. So time dilation means beyond lifetime get increased coming from cosmic rays. That is different thing. That is from time is getting delayed. Okay. So The example of time dilation. Right? So time dilation is fine. This concept of relativity, that is possible. But relativity does not say that time travel is possible. Right?
It's a big question, the opening question.
Yeah. So that was saying. Time travel is not part of relativity.
Yes, I got it.
It's time may change depending on the velocity.
Yes.
But you can travel in time, that nobody is that. So we cannot comment on that.
Sonali ma'am, there is a last question. We cannot take more questions due to time constraint. So the question is asked by Keshav.
Yes.
This is very interesting question he has asked. Can relativity theory be explained using quantum theory?
Yes, special theory of relativity is being used. Quantum mechanics and special theory of relativity is used. There are studies, but quantum mechanics and general theory of relativity is not used. So when we use quantum mechanics and special theory of relativity, that's another subject. That is the quantum field theory or relativistic mechanics. And when we use quantum mechanics and general theory of relativity, it becomes quantum gravity.
Yeah.
So these are the two subjects. I hope the question is.
So I think we should.
Yes.
Yes.
Keshav, are you there? You can unmute yourself if you need more clarification. Keshav. He said thank you,
Okay.
ma'am.
Okay.
Actually, the answer.
So I really don't know students who are there, what their majors, what their minors, or what they will go into. Like anybody will become engineers or will go into the industry. But today my main motive was to, you should certainly learn the biggest and most interesting revolutions till date, whatever it has been today. Certainly you can also always switch to whatever thing you are interested in. So it was a great discussion.
Yeah,
We can also
Sanjay sir?
take the question answer session. The page is there. You can always put up a question there.
or maybe
AIP
next
has
session.
a
Yes, ma'am.
yes,
Yeah,
yes.
question
You can go ahead.
Yeah, question answer we can take, and whatever questions are being coming last 7 days, next 7 days, next talk we can take them. So before we starting the talk, we can answer the questions who are coming through Google Form, right? So you will be there, so you can take the question for 10 minutes, 15 minutes, whatever time it will take, and then we can start our next talk next week, maximum. That is right. So I think
Okay.
who are shy, who are not asking questions here, they can ask later. Doctor, someone has raised hand.
If anyone has a question, you can unmute and ask the
Ask.
question.
Dr. K. Dhan Bhalan is raising hand. Can you please unmute?
Yes. Anybody wants to ask that can unmute and ask.
Please unmute and ask the question.
Or else we can take the question in the Google form also.
Yeah. Thank you so much, Sonia, for wonderful talk. And it was pleasure to
Thank
receive
you.
you. Really enjoy.
Thank you.
Personally, I enjoyed a lot. So I hope everyone would have enjoyed. So now, Sanjay sir.
Thank you to all.
Thank you, sir, for joining.
Thank you,
Now,
everyone.
Sanjay sir.
Yes.
Now, Sanjay sir.
I think Dr. Saab is there. Please ask question if you have. Please unmute yourself and ask the question if you have. Your mic is off, sir. Please unmute your mic. Yeah. Yeah, there is a question in chat box. Ankit sir.
Is there
Yes,
any
question is
common thing between our Veda and Upanishad philosophy and quantum theory? When you are asking such a deep question like Vedas and Upanishads, I don't know I am the right person to answer or not. There are some things which has come from Upanishads, but I really don't know because I need to go back and read the history. I cannot just comment anything just because I have little knowledge. So yes, there are things which has come from Upanishads. Like I have heard speed of light has been come from Rig Veda, and sort of that string theory has come. But then again, I cannot say much on this because I have no opinion on this. Like if we can combine quantum theory and Upanishads or Vedas, it's a very deep question.
Ashwini, Mr. Ashwini, I think Dr. Captain answer this question. You can contact personally in the group, right? Actually, this type of question, I think we cannot discuss at this platform.
Exactly, sir. That is my point. So
Yeah.
there is one's belief, like someone following
It's
Hinduism.
exactly.
Yeah,
We can correlate, we can get the connection, but we cannot prove that.
of course there is a reason. Of course there is a reason, but I think it should not be discussed at this platform.
Dr. Lakshmi Mamila, you can ask question. Please unmute yourself.
And
Good afternoon, ma'am. Am I audible, ma'am?
Good afternoon. Yes, yes.
Actually, generally we think about some issues at that time. Simultaneously, we'll get either. That means, for example, let me take one example. I'm thinking about my father. At the same
Yes.
time, that means within 2 to 3 seconds, I got a call from my father. In the same way, when something we are discussing, then in our mind, simultaneously we get solution for that. Is it, that means whatever the waves are going on in our mind, is it related to quantum
Yes.
mechanics?
Yes, yes, you can definitely relate this to quantum mechanics. So quantum mechanics is everywhere. It's like superposition of thoughts and informations, everything, whatever is going in mind. It has a correlation that somebody asks about the meditation and quantum theory. It's something like that. So
Okay.
yes,
Yeah, thank you. Thank you.
for more you can definitely check. There are lectures because I have seen recently on this thing, like how you can combine your thoughts with quantum. There is this interesting like a video you can search in YouTube. There
Yeah,
is
thank you,
yeah,
ma'am.
yeah, we can always combine quantum with our thoughts.
Thank you.
Someone asked a
Aliban,
question.
there is a question in chat box.
So there's another question. Can we assume a singularity as a particle and use quantum and particle physics to study it? Can we assume a singularity as a particle? Singularity is always associated with infinities and divergences. I don't think I can answer to this
If we
because
say singularity attached to particle, then you cannot define a particle because you cannot define
yes,
singularity. In a solution is undefined in singularity, right? Any solution. So particle is defined by one solution, quantum solution. So if there is no solution, then you cannot define a particle. Then how you can use quantum mechanics or particle? It cannot be done.
yeah, I guess it cannot be because there is no sense of like attaching a singularity to a particle. I don't think.
Because we use mathematical function to define a particle, right? But in solution of any differential equation, but in singularity, you cannot define that. All the analytical function tends to zero at singularity. So hence,
Yes, yes.
zero, then there is no particle, nothing. There is no any kind of shape or phase or anything defined. Then we cannot study. Okay. And
So, Dr. Captain, if you don't have any question, you can conclude the session.
okay, so thank you everyone for joining, and thank you once again, Naliman, for wonderful talk. It was very inspiring and motivating. So let's meet next week with some other talk, and be prepared for questions coming through Google Form. They can take those questions you can take up in the next session. So Google Form, people may ask the questions. So I think Uncle Sir has shared the Google Form in the group. So people who have any questions, so that after watching the YouTube link, the recorded video, recorded talk video that we have recorded, if they get any doubt, they can ask, they can send their question to Google, so we can take them next week. And so as for now, we will discuss. So thank you everyone once again.
Thank you all. Thank you, everyone.
Thank you, Sonali ma'am. Thank you, participants. Thank you, Ankit sir. Thank you, Dr. Captain.